Hi, everyone. I'm Márcia, I came from Portugal. And first of all, I would like to thank the organization for the opportunity to be here to present part of my PhD work entitled Bacteriophages as biocontrol agents against foodborne bacteria in different food matrices. So nowadays, foodborne diseases are a serious health problem. These diseases can be caused by several microorganisms, including bacteria. And the recurrent use of antibiotics, namely in animal production, significantly increases the appearance of multi-drug resistant bacteria. And these bacteria can cause food deterioration and, more important, infectious diseases to humans. Furthermore, the ingestion of antibiotics together with food can lead to the decreased effectiveness of many antibiotics applied in human medicine. E. coli and Salmonella are among the most commonly reported bacteria in food outbreaks in different matrices such as milk, meat, and eggs. And the symptoms associated with food poisoning includes fever, nausea and vomiting, stomach pains or cramps, among others. And despite the available decontamination methods, bacterial food contamination continues to occur. Also, these conventional methods have associated disadvantages, such as changes in the organoleptic food properties. Thus, there is a need for alternatives to conventional methods. Phages have proved to be an effective alternative to conventional methods to inactivate foodborne bacteria without affecting food organoleptic properties. Therefore, in this study, we aim to evaluate phage potential against three common foodborne bacteria, E. coli, Salmonella typhimurium, and Salmonella entritidis, in different food matrices: milk, ham, liquid whole egg, and eggshell. For this, in all assays, a phage control containing only phage, a bacterial control containing only bacteria, and a sample containing both were included, and different values of multiplicity of infection were tested. Both controls and samples were maintained at 25, 10, and 4 degrees, and over time, collection of the liquids were performed and then seeded. After incubating the plates for 18 to 24 hours, bacterial quantification and phage quantification were performed. Since phage efficacy in food depends on phage viability under different conditions, we also evaluate the viability of the different phages tested in food under different values of pH and temperature. So to evaluate the impact of pH, we incubate the different phages at pH 3, 5, 7, and 8 at a constant temperature of 25 degrees. And to assess the impact of temperature, we incubate the different phages at 4, 25, 37, and 45 degrees at pH 7. Then over time, we collected a liquids, serial dilutions were made and then seeded. And after incubating the plates, each phage was quantified. So regarding the results using phage PHT4A against E. coli in milk at room temperature, it is possible to observe a reduction in the sample relatively to the control of around 4 log after 8 hours for both multiplicity of infection of 10 and 100. At refrigerated temperatures, it is possible to observe a lower and later reduction of 1 and 2 log at 4 and 10 degrees, respectively, after 48 hours at a multiplicity of infection of 100. In ham, artificially contaminated with E. coli, it is possible to observe that at 25 degrees, a reduction of 2 log, around 2 log, was obtained after 24 hours of treatment at both multiplicity of infection of 100 and 1000. An interesting fact is that this reduction was lower than the obtained in milk. So highlighting the fact that the inactivation is not so easy in solid matrices compared to liquid ones in milk. Now at refrigerated temperature of 10 degrees, a reduction of around 1 log was obtained at 48 hours at the multiplicity of infection of 100. So now regarding the results with a different bacteria and a different phage. In milk at 25 degrees, a reduction of around 4 to 5 log was obtained for both multiplicity of infections tested. And at the lower temperatures at 10 degrees, a reduction of 3 log was obtained after only after 72 hours. And at 4 degrees, unfortunately, no difference were observed between bacterial control and the sample. Now, for the same bacteria and phage in liquid whole hag at 25 degrees, a reduction of around 2 log was obtained after 12 hours of treatment at a multiplicity of infection of 1,000. And to the same value of multiplicity of infection, this time in eggshell, a reduction of around 1.5 log was obtained after 8 hours of treatment. So now, for another bacteria, Salmonella enteritidis and phage Phages CP1 at 25 degrees in liquid whole hag, it is possible to observe a moid-dependent bacterial reduction. So the highest bacterial reduction was obtained for the highest tested multiplicity of infection of 1,000 after 12 hours of treatment with around 6 log. And it is important to emphasize that after 24 hours, there is also a considerable differences between the sample and the bacterial control. So this suggests that egg components and phages may act together and having a combined antibacterial effect. Now, regarding the stability results for phage, E. coli phage pH84.1, at different pH, at pH 7 and 8, phage remains stable, and a decrease of around 2 log was obtained at the lower pH of 5, and the highest decrease was obtained at pH 3 with a reduction to the detection limit of the method after 10 hours of incubation. Regarding the impact of different temperatures, at a temperature of 4 and 25 degrees, phage remained viable for at least 56 days. At higher temperature of 37 degrees, a decrease of 3 log was obtained. And at the higher tested temperature of 45 degrees, a reduction to the detection limit was observed. Regarding the stability results for Salmonella typhimurium phage PHC SE5, at pH 7 and 8, this phage remained viable for at least 56 days, and a decrease was observed at a lower pH of 5 of around 3 log, and the reduction to the detection limit of the method was obtained after 4 hours at pH 3. The impact of different temperatures on this phage viability at 4 and 25 degrees, as with the other phage, this phage was maintained viable for at least 56 days. And at higher temperatures, 37 degrees, a reduction of around 1.5 log, and at 45 degrees, a reduction of around 5 log. Now, regarding the stability of other phages, Salmonella enteritidis phage pH SCP1, at different pHs, so this phage remains stable at pH 7 and 8, with only a reduction of around 1 log at the lower pH of 5, and the highest decrease was seen to a pH of 3. However, the reduction to the detection limit of the method was obtained after 10 days compared to the other phages, the reduction with the other phages in hours at this pH. The impact of different temperatures on this phage viability. So this phage remains stable under almost all temperatures, with only a reduction of around 1 log after 56 days at the high tested temperature of 45 degrees. So to conclude, as a take-home message, each phage was effective in inactivating its specific host bacteria. The effectiveness was matrix and temperature dependent. Higher bacterial inactivation was obtained in liquids compared to solid matrices and at room temperature compared to refrigerated ones. Refrigerated temperatures were more effective in slowing bacterial regrowth, and stability under different conditions was phage dependent, but in general, a greater decrease was observed for lower pH values and higher temperature values. So overall, the use of phages for foodborne pathogens inactivation seems to be a promising and eco-friendly approach to improve food safety. So finally, I would like to thank the team and the entities involved, and especially in the financing this work. And last but not least, I would like to thank you all for your attention.